let's start. So I've briefly titled the talk 3M. I was a bit ill recently, so you'll be listening to my not so ASMR voice today. Before we start, I must say that those of you who grew up in USSR may know this logo. So we're not going to talk about Ponzi schemes today, even though this was frequently suggested. We're going to talk about something much, much cooler, as cool as like this XXX movie thing, not the kind of movies you thought, but like the one with Vin Diesel. I almost wanted to make a tattoo like this on my neck today for like the epicness of the presentation, but my team suggested that they will all quit if I do. So I decided not to. A bit of introduction, and I guess we'll win a little bit of time until the rest of the kids come. I do not design models on daily basis, at least not now. These days, I'm mostly coding in C++ and assembly. We design the whole stack of different technologies for efficient data processing. But I also love building neural networks from scratch and like coding them in C++ and assembly. And in maybe like say 5-6 years ago, I used to design some of like the earliest designs of graph neural networks and recurrent mechanisms. So there was a lot of flexibility in the size of the input, but there was not much variance within the modality that matches one neural network. Today, we'll try to challenge this. So I'm not a super big fan of, let's say, statistical machine learning or like deep learning, but it's important to keep like your hand on the pulse and try to track what kind of models are we using today. So I will start with like the fun part and the interesting part, and then we'll go slowly into like a slightly more technical things. So just to convince you that this stuff is becoming more and more popular. So there was this paper on April 13th, hierarchical text conditional image generation with clip latents. Those pictures are exactly from the original paper. Those are not the ones that were generated through their, let's say, Twitter API. And this was published in April 13th. Just 1 month later, we get the next model that improves on state of the art, and breakthroughs in this industry, or at least improvements in state of the art, happen essentially every single week. I have this tendency to prepare slides in the last minutes, like right before the presentation, and I'm glad I did it the same way this time, because if I started 1 week earlier, some of the links that I will be showing today will not have been published. And some of them are not even officially published now, so look for weird dates on the slides. So this multi-modal research is like very easy to grasp for people who are not even, let's say, practicing machine learning on a daily basis. And there are like hundreds of Twitter threads just comparing the performance, or I should probably say evaluating the performance of modern models with common sense or community judgment. So it's very hard to evaluate those kinds of models. So people just rely on how affected the people on the internet are by the generated images. So we'll slowly go from less interesting to more interesting prompts and examples. So there were 3 models that this guy, Fabian, compared on Twitter. One of them was Midjourney, another one is DALL-E 2, and the third one is Stable Diffusion. All of them have slightly different purposes and slightly different target audiences. So some of the networks were designed to, let's say, help content creators or content generation companies, maybe companies like Pixar, Disney, more like Midjourney. So I will read the title, the prompt, and you can just focus on the images to see like how much they differ depending on the complexity of the prompt. So Beatles Lego set, catalog photograph. A human anatomical heart made of flowers, pastel, mate, masterpiece. A spooky 1970s floor plan of a haunted house. Worn paper, scary atmosphere, pain, and regret. We already see it takes a little bit of craftsmanship to describe what exactly you want the network to generate. But it doesn't end there. Pixar movie scene of a dark skull wizard fighting against Kermit the Frog as a gladiator, the incredible render presto. So this guy on Twitter describes himself as a prompt master. Whenever I try to describe anything I want to a neural network like this, I fail. Let's go further. So behind the scenes of shooting the moon landing, Hollywood studio in 1969, backstage photograph, astronaut actors, lighting. Um, Vaporware, underground swimming pool, digital painting, Procreate, CG Station, 8K Blender, hyper-realistic render, 3D Photoshop, award-winning digital art. I'm not even sure I know half of the words here. And then we got from, let's say, 2-line prompts to 3-line, 35mm hyper-realistic product hardware render of a strange dark electronics device made entirely of large salt crystals, salt crystal interface, transparent, sci-fi, dark, atmospheric. And we start noticing that people use like those prompt adjusting suffixes like atmospheric or digital art. I would use them too. So this one is my favorite and probably the most complex of all. Film still portrait of an old man, wrinkles, dignified look, great silver hair, peculiar nose, wise eternal wisdom. I guess it should have had Armenian nose. Eternal wisdom and beauty, incredible lightning, and camera work, depth of field, bokeh, screenshot from a Hollywood movie. So yeah, it gets a bit too complex for me. I tried myself, so I guess many of you would have a demo of DALI 2 or similar neural networks. So I tried tweaking Mona Lisa-like paint, like generating Mona Lisa-like paintings with different faces. I guess one of those can go like on a poster on the wall and one in our office. And it's not really even that much of a cherry picking. So having access to the beta, you can generate hundreds of pictures like this and then select the best one. I guess to get those 2 pictures, I had about 12 images generated with similar prompts. Like on average, they look something along those lines. And 2 out of 12 is not that bad, 1 in 6. And I then tried this thing. So DALI 2 performs real well when you try to mimic some famous artists. I tried software developers in Armenian dresses by Klimt, but many of you may know the Kiss painting by Klimt. This one kind of resembles it, something between a shepherd and let's say a software developer, like handling laptops, having laptops in their hands. Looks fun, but it's not always that easy and that beautiful. So there was this Midjourney paper, and then there were a bunch of papers later, or a bunch of models later. One of the most recent ones is Stable Diffusion. I guess it was published like a week ago or so by Stability AI. And we run that same model with the same prompts that we had for DALI. And even though generally papers that and models that come later improve on the previous result, there is a lot of dependence on the specifics and the style of the prompt. So those same queries yield, well, I don't want to say garbage, but not really as good as previous results. Okay, so enough with the fun part. Let's get a little bit more technical. So when we talk about multiple modalities, I would generally split them into those 3 categories. The first one is kind of the most obvious. You translate between 2 modalities. So essentially, imagine like the old school task of neural machine translation. You have like a sequence-to-sequence modeling problem. You can do the same across modalities. So you can have an input image, and you would generate a sequence of textual tokens, which will be image or let's say video captioning problem. And in the past, we would try to solve problems like this and the many others on the list by a combination of very different architectures. This talk that I've prepared, during the process of preparation, I found some really amazing resources. And one of those was my teammates found those resources, was the ACL demo by DeepMind on multimodality. And it's in 3 parts. The first one is the past, the middle is today and like the current, and one more part for the future directions of work. Today's talk is somewhat shorter, so we will not talk about the past too much, but in the past, they would take like a lot of different CNNs, let's say for different frames of the video. Then they would encode the context of every frame. Then they would run an RNN through the embeddings of different frames. And then they would have another, let's say, sequence generation model at the end. So a lot of composing of different architectures is not really happening today anymore. Today, most of the points on this list are transformers. The primary differences would be like if this is encoder only, encoder decoder architecture, and what kind of modalities they take in or spit out. Another one thing is like text to speech or text to code. Text to code is a bit of a weird domain. We'll talk about it later. So like text to code, to me at least, seems like text to text, and we have debates in our team regarding this topic. And then there's like complex content, which is a bit of a weird title. I didn't find anything smarter. Imagine having a context that involves a lot of information. So let's say when kids just learn the basics about the world around them, they get the input in the visual form, they get the voice input from, let's say, their parents describing something. So it's already multiple modalities mixing both in inputs and in the outputs. It's not like one-to-one mapping from two different modalities. Today, we have neural networks that operate on complex dialogues that contain a lot of bits of information in different states. We'll briefly cover those, but then most importantly for, let's say, my company is the topic of, let's say, non-generative models and most importantly, semantic search, which largely builds on the same encoders at least, so we do not use decoders too much. For you to get a wider understanding of, let's say, how big multimodality is, this is just like from one single paper, Multi-Modal Learning with Transformers, a survey. The modalities are listed on the left side, and this would include everything from, let's say, point clouds and sketches to SQL database schemas, speech and audio combinations. And the number of papers that's being published these days on this topic is just tremendous. So we'll not cover everything, not by any chance. We'll focus on a couple of primary architectural differences between those designs. We'll talk about the zoo of the model that was, let's say, produced by different combinations of those architectural choices, not inclusive, obviously. We'll cover some of the data sets that are used to train those kinds of networks and the big challenges that we face. But all of this will be in a horribly mixed order, so I'm sorry for that. So the first part is like I mentioned that today all of those architectures are just like transformers all around. Well, if we say transformers, the most important thing to remember is attention-based neural networks. The question is, how do you apply attention? So if you work, let's say, on two modalities, you would have a choice of, let's say, having two separate towers, one for images and one for text, and the information will be propagated separately, being contextualized in every following layer in a way matching the specific modality, but that is not the only way. So one of the most important kinds of research that I love is trying to, let's say, not combine every good idea, but trying to, let's say, prepare a complex overview of the effects of every design choice. And there's a paper just about that, decoupling the role of data, attention, and losses in multimodal transformers, also by DeepMind from last year. And they talked about two things. First is mostly attention mechanisms, and the second is loss mechanisms. And when you have attention-based neural network, well, the obvious thing, what you can do, you can have, let's say, again, the two separate channels through which the information will be going forward. And the tokens of text input will not be attending, let's say, the inputs or the tokens of the visual input, and vice versa. But you can do, let's call it, let's say, the merge attention. That's the way they call it. When every token in the sequence, both visual and textual, is provided as input into the same layer, and the attention is applied across all combinations, all pairs within the same layer. So like every visual token attends every textual token and every visual, and every textual also attends both visual and textual tokens. Surprisingly, they also took the courtesy of comparing merged attention to co-attention. That's the mechanism when every token only attends the tokens of other modality. So let's say if it's a text token, you only attend the visual tokens. And one of the most interesting results is that this co-attention mechanism ended up working oftentimes better than the merge attention mechanism on a bunch of tasks. So in the left bottom corner, there's this table that showcases like how co-attention often performs, let's say, a couple of points better than the merge attention, which is not making that much sense. So it would obviously be computationally more efficient to only attend part, but getting higher accuracy in the meantime is a bit weird. And just for clarity on this slide, on the next one, MMT stands for like multimodal transformer. And their architecture, at least according to paper, mostly resembles a Wilbert, but they do not explicitly describe all the parts of the architecture that was used in this kind of comparison. Another part of the story is the losses. So especially if you have two modalities being propagated through the same layer, it's not obvious how the loss would change. They cover three kinds of losses. The first one is like pure text. The second one is just images. And the third one is the matching part between the images and the texts. And this can be done in a couple of ways. The one is the most obvious, I guess, for like people who practice classical machine learning is like the binary classifier. The one that is more important for the purposes of this talk and the one that we'll concentrate on is the contrastive loss. So when we talk about contrastive loss, there's a paper that is easier to start with. So contrastive losses are not used exclusively for multimodal stuff. They're used throughout the industry for even single modality inputs or single modality architectures. Probably the most famous bimodal encoder architecture in the past couple of years was CLIP by OpenAI. And the idea behind this neural network is that you have two separate towers. In the original paper, that would be, let's say, a transformer, BERT-like transformer for the text input, and a ResNet for the image part. It's not true anymore. So like even the image part is a transformer today. You would propagate the information through those two towers separately, and then you would add an additional block that is responsible for the contrastive loss to actually learn how to match the outputs of those two modalities. And as many things in machine learning, a lot of the stuff that is being published today, at least to me personally, resembles like very old school ML or computer science results. So coming more, let's say, from, let's say, discrete algebra space and then, let's say, graph theory, I immediately remember like graph drawing mechanisms and the ways how we can, let's say, reduce dimensions. There were works by Tute and Edis going back as far as, let's say, 55 years that had shown, let's say, force-based algorithms how we would draw graphs. And if you, let's say, build up a graph where you'll have two kinds of nodes, one of them will be images and the other one will be text, and you just add edges between the nodes that match the same object or similar objects, this contrastive loss thing is essentially the force-based algorithm for drawing this graph in any number of dimensions. But most commonly, most graph processing packages today would draw them in 2D. So the idea is very simple. You have multiple iterations, and in every single iteration, you do a set of both attractions and repulsions. Attractions are only done on pairs of elements that are linked with each other and are kind of connected. And repulsions are done on all pairs of elements. So essentially, every iteration would have quadratic complexity in the naive implementation when you try to repulse everything from everything else. But again, as it was shown many times in the, well, maybe not so many, but a few times over the last years, we can learn a lot in ML from the work that has been already done like 50 or 60 years ago in broader science, and including numerical sciences, which were just appearing back then. And later we'll talk about some of the challenges that people get by not using those basic ideas. But the very first challenge I want to cover is the training costs. So those experiments are exceptionally costly and hard to organize. I found somewhere, even though I don't think it was in the original paper, it was somewhere in the discussions on the internet, that the original clip, well, this is obvious, it was trained on 400 million images, but they claim it took about a month on roughly 600 GPUs on the V100s. And it's not that the setup that every AI researcher has available to himself. And as we show, like, if you have so many attention mechanisms, if you have so many loss mechanisms, if you have many modalities, well, you obviously get a combinatorial explosion in a number of different experiments you can run. I'm not even saying the number of optimizers you can select, the learning rates that you need to know how to update. And my colleagues here in the room as well know all the horrors of having to restart the experiment once in every few days because this learning rate doesn't apply and the automatic way of, let's say, updating it doesn't work. So that's the pain of doing pre-trains. And between every couple of those iterations, unless you are NVIDIA and you can train BERT in, let's say, 16 seconds on a few thousand GPUs, then the step between your iterations would be a couple of days. And it's very complicated to experiments like this. Because the experiments are so expensive, it's wise to use the knowledge of the industry, the broader industry. And there's this amazing blog by Lilian Wang that many of you already know. And she covered contrastive losses quite deeply a few months ago. I think it was in May. And there are a few primary points that she makes, and she references a few brilliant papers. The first one is avoid false negatives. And this is like the primary pain point with contrastive losses. So if you, let's say you pick a batch of 500 entries in every batch, this means you'll be computing 500 by 500, which is how many? 25,000? No, 50,000? Yeah, I think 500 by 500 is 25,000. 4 zeros, 25,000. 25,000 distances. And you better make sure that within this batch, for every entry, you have exactly one positive example. But when the batches become big, which is necessary for training models like this, and this is like the third pain point, if you make batches big enough, it's likely that you'll get false negatives within the sample, and this will destroy like your entire training pipeline. And again, one of the things that we should consider is like how this like high-dimensional space looks. So if you want to try to bring points that match to the same object close to each other, maybe it's wiser to, let's say, put more emphasis on the attraction part rather than repulsion. And when you're doing repulsion, you must make sure that the repulsion is kind of balanced and not like shifting everything into one single direction. The second point, which is more like of an empirical result, is that you have to heavily augment your data. There are a couple of examples that show qualitative improvements, especially on the image encoder side, both for ResNets, ResNet heads and both for visual transformers, that say that you must try to both change the color scheme of your images, aside from like the classical augmentations, such as like rotations and cropping, and this yields significantly better results. So as I mentioned, this batch selection part is highly tricky. There was a paper from MIT, debiased contrastive learning, when they tried to actually properly filter the contents of every batch selection. And the M number on this chart essentially describes like how many entries like were removed, or let's say positive or negative samples were added within the batch. And as you can see, even from the TSNE visualization, which is obviously a lossy representation, so it will not show all the proper information about the final vector space, we already get a tremendous improvement from debiasing the batches. So let's talk about multimodality, because it was the title of the talk. I don't want you complaining that I misled you into like attending the talk you didn't want to go to. So going from 2 modalities to 3 sounds like an easy step, but we do not have, let's say, an interesting clip matching way of how we do it. So the best idea so far is just like to freeze all the other towers and learn the new modalities as attempts to map any input object into the space that is already learned between the 2 modalities. And as with this audio clip paper, what they do, they try to freeze, well, they freeze both the textual and the image heads and train the audio part. In this specific example, they get to outstanding results for understandable reasons. So they take EsResNet, EsResNext. This is the model I've never used myself, but the training sample that they use contains environmental sounds. So if you have a clip model that is already trained on, let's say, things such as dogs and cats and their textual descriptions, those are things that are relatively easy to find mappings for in the environmental sounds data set. So if the sounds would have been much more complicated dialogues, you may not have been able to find a corresponding style descriptions for images or for text in the original training data set of a clip, and the result would have been bad. So before going forward with some of the challenges, I want to mention that this semantic search thing that we work on, it doesn't even need decoders. We can rely on encoders only. And to build up a good semantic search engine, you essentially need 2 primary components. And the first one is shared space embeddings. So you can put every modality into the same vector space. And the second one is a good engine for approximate nearest neighbor search. To clarify a little bit, when I say good shared space embeddings, there's like a number of approaches you can take, and even very simple ideas sometimes work great. So the first one I want to mention is Seam CSE. They do not use supervised data. It's a very interesting approach when they just propagate the textual information. It's not even multimodal, it's just a single modality text. They propagate the information through the neural network, but they propagate it, let's say, twice or multiple times, enabling dropout with different noises. And essentially, they train a model for, let's say, semantic text, STS stands for semantic text. Yeah, semantic textual similarity. Thank you. By trying to bridge, or let's say, bring together the outputs of a neural network that would work on different noisy input. But the noisy input part here is a bit tricky because we are not really augmenting the original data. We're augmenting the neurons or the state of the neurons within the neural network, which make this approach generalizable to more modalities. So let's say augmenting the neural network, or let's say adding this dropout, would be identical both for the visual transformer and textual transformer. There is no transformation on their text or image itself. The second thing is like sentence BERT that I guess everyone already knows. So like you would have, let's say, two separate towers, but the weights between those two will be shared. And you would have a supervised data set of pairs that you would learn to bring together. And then this idea would have been amplified further towards CLIP when you have those pairs, but one of the objects in the pair is of a different modality, such as images. And when it comes to approximate nearest neighbor search, there are like a couple of go-to modalities. I guess this is even like closer and more interesting to my personal domain, like approximate nearest neighbor search and like large sets of point clouds. But we're not going to talk about them today, just to say that there's FIAS and SCAN as like a couple of go-to libraries for those indices, one from Facebook and one from Google, understandably. And if you want to build, let's say, a semantic search demo, and we may have one at the end of this talk, these are the couple of libraries that you will use. So the third and the most important challenge to me personally, one of the most interesting challenges in ML for myself, is the quality of those embeddings. So when we take a BERT or a model like BERT, there's a number of papers that have shown that those models that are trained on masked language modeling, they produce anisotropic vector spaces. So they are not uniform, they're not equally spaced between the points, and this is a big problem for any semantic search application down the line. And there are a couple of artifacts that are further studied in some of the even earlier papers. Some of them go as long back as like 2013, 2014, right after the original Word2Vec paper. So some of them would say that, let's say, if you use a cosine similarity metric, you would produce artifacts related to the word frequency. So essentially, you have the origin of your vector space, and the words that have that are less frequent will be further from the center of your origin. Essentially, the amplitude will be proportional to the inverted frequency of the word. And with the hyperbolic spaces, yes, you will encode some of the hierarchical dependencies between the words, such as, let's say, an animal and a human. So let's say one is a kind of another. But yes, we've learned some things about those vector spaces and their properties, but there are issues to be solved. One of them is, let's say, building the space uniform so that a semantic search engine down the road, it can be hierarchical navigable small world, it can be locality sensitive hashing, it can be KD trees or anything like that. For it to work properly, you need to add uniformity into the space. And how we do it? Should we add a new loss function? Another thing that crosses my mind frequently is having some sort of a Lipschitz constraint on the towers themselves. So imagine propagating information through the neural network, and if you add a tower on top that would bridge modalities and bring them into one shared vector space, you would be losing some of the information from the original space. So essentially, like a pre-trained model on the language task, this model later fine-tuned for like multi-modal semantic search. So you'll be losing some of the information. What if you could add a loss that preserves some of the constraints from like the original model, such as that if you put two inputs into the neural network and you know about them that the distance between those inputs is kind of a certain constant, you would kind of put a constraint on the fact that after the final transformation and the rotation of the vector space to be aligned with another vector space, the distance between the original inputs will have to be changed by not more than a constant factor. So this is what the Lipschitz constraint would be. And I think I've seen some of the initial work in this direction, but not even remotely to cover all of the potential ideas. And another thing is that, yes, we have the STS task in the famous benchmarks for natural language processing problems. We may not have as good of a benchmark for the multimodal thing, but if we're doing, let's say, end-to-end semantic search, isn't it better to add an end-to-end loss, like building up a semantic search engine, essentially an index, and trying to train to minimize the recall, or let's say maximize the recall of the search engine. So there's been work in this direction. The two of the most interesting papers both come from China, one from ByteDance and the other one from Tencent, 2020 and 2021. The first one was introducing the concept of normalizing flows, and then the paper and the network was called BERT flow. This was later improved by the procedure which is called whitening. To me, it seems like just adding a singular vector decomposition into the propagation of information through the neural network. So they do both the dimensionality reduction and add some properties into the flowing signal. What they have shown is that there is a massive improvement on the semantic text search tasks or semantic text similarity tasks if you do this kind of procedure. So this wasn't just a pure speculation that you need anisotropy in the space. It was actually proven. And with quite significant improvements, like 5–10% improvements over previous state of the art. So just to further show how much better it can be. So we've talked about BERT flow and the whitening, but there's also this CSE when we did drop out on the information that propagates through the network. Such a simple trick. It's entirely unsupervised. You don't need any data preparation or anything like that. But they've, again, showed massive improvement even over like the whitening procedure on top of Roberta. So going from 46.99 points to 69.87 points with just a little bit of noise on text. This is massive. So the third and a half challenge, I guess. So this is not entirely different from the previous issue. If you were not sleeping, it was quality embeddings. This one is quality baseline embeddings. So if we're freezing all kinds of modalities to add them into like the broader multimodal network, we must at least make sure that the original modalities on which we are trained produce a good enough space. And when I say good enough space, there's like an issue not just of the final points, but also like of the training data set that was used to produce it. So when you train on big modern data sets, the style in which the images will be described will be vastly different. And if your modality that you're trying to add is audio and you're adding stuff like dialogues, and the dialogues would have a pair of the WAV file and the textual description, or say the transcript of the talk, will have massive issues if the style of this dialogue doesn't match the style of the narrative or the captions of the images. So the captions can have, let's say, short descriptions, such as the two people are walking down on the beach, or can have much more scenic, much more, let's say, descriptive, long descriptions like the one on the right. So we slowly come to the topic of multimodal data sets, as in many places in machine learning, we've started with like fully manually annotated, but yet small data sets, and like MS COCO or Microsoft Common Objects in Context is the best example of that. It's 300,000 images, all of them annotated and more than in one way. So yes, they have annotations for object detection, but they also have 5 descriptions for every image. Not that they are vastly different, so it's not like one of the descriptions is short and the other one is like very scenic. Those have like kind of similar lengths. We've immediately outgrown the abilities of those like tiny things. So I guess it makes sense to introduce conceptual captions by Google. Those are 3 million images. They are taken from basic internet crawls. So as it often happens, we just take dump of HTML files. We parse them with, let's say, something like beautiful soup. We find image tags, and within them we find the alternative text properties. And this is even like the most basic form how you can do it. HTML files include so much more hierarchy and context that we just skip. even like the most obvious thing of taking the nearby text, or at least the title of the page, may have been a better way to prepare a training data set than just this. On the positive side, the data set comes with at least some basic statistics that you have on average like 10 tokens per caption. And they also annotate those images with some automated methods. And for those automated methods, like they label the images and they also add the confidence score for the label. So it's not nothing. Clip changed all of this by scaling it up. So from 3 million images to 430 million images. So it's over 2 orders of magnitude improvement. Clip was later superseded by the Lion 400 million, which is like open crawl, an openly gathered data set, the one that we use and like its bigger versions to train or pre-train our models. They are also, again, gathered automatically. The images themselves form a package of 10 terabytes. So this is significantly bigger than the average hard drive or SSD. So this is already putting a certain constraint on where and how you can train those. And sending the data over a network from, let's say, your local store to AWS, where you may want to train the networks like this, is maybe even costlier in terms of like the networking costs. The great stuff that Lion did, they've filtered the images so that the alternative texts are at least 5 characters long and the images are at least 5 kilobytes. Obviously, they would have to shrink them afterwards. They deduplicated the URLs so that the data set is nicer. And again, you would have a lower chance of negative samples. And they did something else. They've used clip model, so the original clip model, to filter the images and the tags that do not match with each other too much. So this is both a good thing, but also a point of controversy, because now many people consider that like this Lion data set and the models that are trained afterwards are essentially just distilling the results of clip, because the data set that you use for training is a product of another neural network. The great thing, they come with pre-indexed KNN files that you can use to build up an online demo just right out of the gate. The bad part, they are only English, but not for long. So I was preparing this talk in the last minutes, as I already told, and some of the content seems to not even have been published. So on the Lion portal, there's this article dated September 9th, 2022. And the first moment I saw it, I thought something is wrong with my head because I was like ill when preparing this. Turns out, no, I've reloaded the page a couple of times. It seems to be this is from the future. So you must trust it. Like in the future, I hope they know what they're doing. This data set has 5 billion entries with 384 by 384 resolution. This data set forms 240 terabyte dump of just images alone. But it's not every network-attached storage system that would have the capacity to store all of this, let alone commodity computer. Great part, it's multilingual, yet not as multilingual as a fair setup would suggest. So just like with Common Crawl, about half of the data set is English only. Another 100 languages form maybe about 40% of the data set. And the languages are annotated by CLD3. So this part is a bit tricky. So if you take Common Crawl data set, for every work file, web archive file, they have CLD scores and labels beneath, as we've learned recently. And it's already annotated with CLD3. But this annotation is for the entire HTML file. So I'm not sure that this distributions match the distributions of alt text itself. So they may have done the easier thing of just taking the language of the whole page rather than the language of annotation. And as we all know, those two things may not always match. One important thing to reference, if you ever want to do experiment like this, there's a package called IMG2 dataset, pretty famous and popular on the internet, that can crawl and gather dataset like this for the training pipeline down the road. So few-shot learning can also be multimodal. And there will be like a set of papers that I will just briefly mention. So there was this approach of Frozen, which was one of the first few-shot multimodal architectures. As you see, all of the input modalities are interleaved. So image, text, image, text, image, text. This would be trained on something like visual question answers, VQA2 dataset with 265 annotated images. But this is like only one of the first works. The more advanced and interesting works would be something like this. this Flamingo network by DeepMind has 80 billion neurons, which seems to be a little bit more than the crocodile brain. I don't know why they call it Flamingo, but a crocodile brain is tinier than the hamster brain. This already gives the network the ability to do inference on sequences of images, non-interleaved, and even some form of basic reasoning on the mathematical subject. So you would show it a printed example of a math query, and it will give you the answer, pre-calculated. So there are also data sets that are formed in a much funnier way. So people designed a game, guess what, where people would have a game of asking each other questions and answering them just to guess what's on the image. And this data set was also publicly presented with 150,000 human games. Another modality is code synthesis, which we think is very similar to text, but it's different in terms of its final procedure. So the input is mostly textual. It's the source code. Sometimes people would try to do abstract syntax tree inputs, and you can also do it with not just text transformers, but also, let's say, graph neural networks. But the post-processing, let's say, working with the output of the neural network is more interesting because you can run unit tests on them, produce a lot of examples, and then this would be, let's say, somewhat similar to the beam search. When you produce a lot of examples in a generative fashion, you run tests for them, and you cherry pick the examples that pass the tests. And because we can do so much, why not bring it all together? I guess that's what DeepMind said. So they designed this network called Gato, which is the generalist agent. It works on RL inputs, essentially Atari games. The way they work with them, they pass them through essentially the same transformer as the image part. Text part. So for text, they use sentence piece tokenizer with 32,000 tokens. And they've added another 1,000 tokens for all the keyboard buttons that you can click when playing games. And then they also use 1,024 unique identifiers for continuous values. So essentially almost everything, every modality that there is, like continuous values, games, and text, goes through the text encoder, somewhat tuned. But everything that is visual is a bit weird because it goes through a different mechanism. They split them into patches like VIT, 16 by 16 pixels. They normalize them in a weird way, but then they do not pass it into a VIT. They pass it into a ResNet block. I guess for efficiency purposes, but with models like this, it's hardly efficient. So this approach of using, let's say, one cornerstone modality, such as text, and then bringing everything to those pairs of, let's say, text with something, was later worked on in Socratic Models paper, also by Google, where they tried to bring language models, visual language models, audio language models, robotics, and even, let's say, daily agent mechanisms into one single mechanism. If you look into the paper, it's exceptionally hard to understand without going through the examples. And when you start looking into the examples, you understand they had to bring up a lot of prompt tuning into every part of the pipeline, trying to merge, let's say, multiple huge generative models together to get an improvement. Truth be told, their improvements on almost all benchmarks they've shown are absolutely mind-boggling. In the last few successive papers, you wouldn't see improvement like this. But then on the opposite side, they take, let's say, 5-10 networks. Let's say 5 networks. 10 is an exaggeration. Even 5 is a bit too much. Probably 3-5 networks that are huge by themselves, and it's almost impossible to even infer them one by one on commodity hardware. And their estimate was that sometimes they would need, let's say, $150 for one set of evaluation tests for just 100 samples. So imagine having 100 samples, and to beat state of the art, you would have to spend $150 just for those 100 images. So this is not scalable by any means. And the problem, why I'm saying it's not scalable, it's not just scalable in terms of costs, it's also not scalable in terms of the logical inferencing capabilities. So just to make sure that we've covered this part, we started in the very beginning by saying that by looking at the pictures and understanding that evaluating them without a human eye is a bit complicated. So even with those two pictures, it's hard for me to tell which one is better. And when it comes to, let's say, proper complex setups, when you need to do causal inference and you need to generate content, you always go from less data to more data, from less information to more information. So unlike our primary domain, when we encode information, so go from a lot to a little, they generate content going from a little to a lot. So they have to produce information, but by doing that, due to the lack or inefficiencies, insufficiencies of statistical models, they are not able to produce good results. And within that same ACL training, there was a great talk by Damien Tenney, I'm sorry for mispronouncing his last name, where he showed with very, very obvious examples of how poorly things like this can work. And multimodality makes it super evident for a human eye of how poorly modern generative models work when you add multiple modalities together. So this is like a dialogue setup. The person is asking, or let's say the training set has a question, is this a fast car? And there are a bunch of cars. It just so happens that most of the fast cars are red, like Ferraris. So when you show two pictures, like a blue one and then a red one, like a modified car, and ask if this car is faster, the statistical model assumes, yes, the car is faster because all the fast cars it's seen is red, but it is not learning any causal information. And us trying to do generative stuff with models that cannot even infer this basic information is a bit of a leapfrogging. And just like to put a little bit more strict, a little bit of a strict condition on why this doesn't work, this is a slide that I haven't prepared. I took it directly from his slides. It's just like so good. And I will just read it to you. Even simple predictive questions should display adversarial robustness, compositional and crosstalk generalization, robustness across distribution shifts. And all of those settings violate independent and evenly, or like equally distributed training test data central to statistical learning. So I tend to think that generative stuff is a bit over our head. That's why we're focusing on multimodal encoders these days at Unum. And if there's something fun to take from this talk, aside from the fun pictures in the very beginning, this is a couple of memes I prepared. So the first one, cross encoders don't scale. This is my personal opinion. Come and fight me. And the second one, contrastive losses is the go-to solution, at least today, until we find something smarter for multimodal models, and it has been around for many, many decades. We're just scratching the surface of their capabilities. So thank you very much, and I'm open to questions.
Promise to be done on time.
Almost. Yes?
Thank you so much for the amazing talk. I was wondering, what are the benchmarking tasks or applicable tasks which you consider will have the most prominent benefits for
So again, as we focus mostly on encoder part, not like on the generative tasks, we need to have STS-like benchmarks that would include multimodality. And within our team, we have a set of benchmarks and data sets that we've gathered together, but we also use a lot of the ready examples. Which ones do we use?
Most is already pre-translated by humans for 10 languages, and for other languages you can make the MMT. So we're trying to do something like that. So you have captions, you have the images, you can translate them, and this is pretty much benchmark.
So this is Vladimir, and I will be redirecting all the complicated questions to him. Yes?
I have a comment about multi-language stuff. There is a text-based model, Bloom, which is international,
Yes.
which is quite big. It's kind of like GPT-3, and in its training set, it has around, I don't know, 60 language, Armenian not included, but Russian is included there, and a lot of code source. I think in the future, you are working on it as well, but in the future we'll see text generating engines and image generating engines that operate on different languages as well.
Well, actually, a little spoiler.
Yeah.
Right now, it's just retraining the multilingual thing, so probably we will somehow source some of the pre-training.
Bloom is open source.
Yeah, we know that Bloom is generative. And
yeah, Bloom is generative.
And like even when it comes to generative tasks, there are like models that supersede Bloom. So like NNLB, No Language Left Behind by Facebook, it includes 20 languages. And the part about including Russian is not that unique. So if you take the Common Crawl split, Russian is almost always within, let's say, the top 3 or top 5 languages within any sample of Common Crawl, aside from unilingual English only. Any more questions? Yes?
Yeah, first of all, thanks for this great talk. And so when you talk about multimodal
So I'm not sure I've seen evaluations specifically for those tricky things like humor and sarcasm for multimodal things, because there's so much to measure with those models. What I may say, or what interests me personally, aside from having those pairs between different modalities, one of the important things that we may want to learn within the networks is, let's say, causality, to be able to do multimodal stuff better. And for causality, it's great to have counterfactual data sets. So counterfactual data sets are almost never multimodal. So you can have them within a single modality. And the next big interesting thing that I would want to see probably is putting more emphasis onto counterfactual learning within one single modality, and then using this pre-trained vector space and this understanding of counterfactual examples for future causality to actually extend it to new modalities by bringing them into this pre-trained main model.
Questions?
Vardanyan? Yeah.
Two questions. First one, in the beginning of your talk, you showed this old tension and heritage tension type of things, right? And I wanted to understand, if you have multimodal, you have tokens of text and you have tokens of image.
Yes.
You do tokenization somehow.
Yeah.
Touch-based.
Yes. And you can fit it into the same input layer. So you would patch the images, you would look up the embeddings, you would concatenate them with the, let's say, embeddings of the textual tokens, and you would fit into the same layer. This is one of the possibilities, but if you, let's say you have two separate towers, you can avoid doing that and just
The same tower.
Yeah.
How do you mix them in the order?
Oh, okay. So same way as you can learn order or spatial embeddings for text, same way you can add those spatial embeddings for the images. So one part would be, let's say, describing the spatial relations between one of them and the other within the second sequence.
You put next to each other, you put text tokens and then image tokens?
Generally first image and then text.
Separators from top.
Yeah.
And the most architecture is like that. You have the CLA token in the beginning, and after that you have the token for the text, the separate token, and after that the token for the image, and you classify the same. They're similar. But
My next question is, where is your demo?
Oh, okay. So I have not one, but two not working demos. And I can tell you more. The first one we prepared internally, and the second one we didn't. So the first one, even though fashion is not my profession, guys at the office somehow thought that let's take the fashion data set. It's about 40,000 of annotated images. So it's small enough for you to do KNN without any advanced indexes, just ingest it into the GPUs, and I guess in 0.3 seconds, so about 300 milliseconds, you would get a bulk similarity metric for all the samples within your data set. And then there's a problem with the widgets there. So we thought, okay, if Y on dataset comes with pre-trained indices, and it's also available online, and it's not even from today, it's from the future, it must work. But when I opened up the website just a few minutes before the talk, I realized that whatever I tried to input into the field, it's not responding. So it's, again, that same challenge of the cost and the complexity of the multimodal work and multimodal research. Our Python scripts, ML scripts, are not really designed to work consistently, be replicable within the span of, let's say, 1 or 2 years or something like that. So the moment we use it to train, next day it's not working. Now imagine having not 1, but 10 modalities and data in the volumes of hundreds of terabytes from different places. There's just so much stuff that can go wrong, especially if you prepare a demo in the last minutes of the talk. So sorry for that.
This is the reason to be our guest in our work. So.
Yeah, so our office and our headquarters is in Armenia. We work on some crazy stuff, joining together advanced computer science research, hopefully cool AI research stuff, and a lot of low-level programming in assembly and GPU stuff. So check out our website. We will be publishing, we already publish a lot of, let's say, state-of-the-art engineering stuff. And this year we'll be starting to publish more state-of-the-art and hopefully improvements in the AI domain as well. Thank you again.